discussions and mixed in with the physics.
Okay.
So, chapter 16 stuff is due tonight. So I'll open up the floor for any questions about that. After that, we'll continue with chapter 17. Yes.
On number, I'm going to try to recall this and get it wrong. How do you find electric potential for a single molecule without, like, it's just like moving along the x-axis? That threw me off.
Which question?
4,
I have
9. Why does mine have a 9 and hers doesn't have a 9?
Who's refreshed the tab more recently?
I mean, I was working on it about an hour and a half
I'm
ago.
on it right now.
So hers.
I don't know. Web design is being really weird with this whole assignment, and I don't like it.
Hold on. Oops. Because if there's not a number 9, then my question is a moot point.
I did add one. Someone in the other lecture did notice something strange about it too.
Please hold, sir.
Insert dial-up noise. What's up?
I can't read what half of this says, so I don't exactly know what changes he wants me to make.
I didn't see the paper you tossed down until after I'd asked.
What class is it here?
It's from our research report.
Okay. Mine has a number 9 still. An electron is at the origin. Calculate the electric potential at point A. X equals some number.
Let's see if I have it.
Maybe I just don't know, like, I definitely just don't know what electric potential is, and that might be helpful.
Yeah, I definitely don't have that.
This is awkward.
Okay. I'm putting a little bit of chapter 16 back up on the board to show where a couple of these formulas are coming from.
I have a new number 9 that wasn't there before.
Yes, I added one because I took some points away from other questions.
Okay.
This formula is about the change in potential energy of a charge as it moves through an electric field. So in a capacitor, as a charge, say, moves from one side to the other, its potential
Oh my God, I
energy
found it.
is
I was so
kinetic
excited.
energy. So this is its energy, this is how its energy changes. I'm going to modify this slightly to become potential energy equals QE and its current location. So instead of change in, this is based on its current specific location, rather it's, well, I'll elaborate further. a second how it relates to the question in mind.
So that's not the change of potential energy, that's just the amount that it has right then?
Yes. That is the potential energy that the particle possesses at that moment.
So would you take the integral of that to get the equation you just wrote under it? You take the integral of the delta, it goes away.
Oh. Yeah, yes. Now, additionally, I'm going to edit this a little bit to make it into the form for voltage right here. You know that change in voltage, which is the change in electrical potential. So this is the potential energy that the object possesses. This is the change in the amount of field potential that exists at that location. This is talking about what the field is doing at that spot. That's equal to delta potential energy over Q equals negative E times delta X, which is really just this formula with the Q moved under the delta PE. But if we remove all the deltas, we can look at the potential of one spot based on either the potential energy a particle possesses at that location or its position within the E field.
Is that on our formula sheet?
Should be.
So, for this one, it gave us X, which is great. Don't have to work with that. But we don't have, it's like not telling us anything about an electric field that's within. That's where I was thrown off.
That's fair. We are told there's an electron at the origin, and we are moving some distance away from that electron.
So E, what is the capital E in this one?
Electric field.
Oh, the electron's not moving.
The electron is not moving. We were examining the potential at this spot caused by the electron being right there.
I see. I was moving the electron, which
That's
is why there was no electric field. But you can use the charge of the electron to calculate the electric field it gives off.
Now,
Or now.
this particle is giving off E field lines, so there's going to be some amount of field at this spot. We know charge of an electron is negative 1.67 at 10 to the negative 19 coulombs. So we need to flash back and look at the equation for how to find electric field based on what is creating it. So that's actually further back. So to find E field, we're going to want K times Q over R squared. Plug this in over here for the E in this formula. Voltage equals potential energy over Q equals negative K Q. I'm going to change this X to an R because it is talking about the radius from the electron, distance from the source, and divided by R squared. So both the potential at that spot, the voltage at that spot should be K times Q times R divided by R squared, which will simplify to KQ over R. I'm gonna check that real quick.
How do we know that that is all equal?
Sorry,
I said, how do we know that's all equal to each other?
all of this?
Down one, yes.
Well, this, all we did was take two legal formulas and combine them. So, you have the formula for E field, we plugged that in for the E field here. And it gives this. This piece, we don't know its potential energy, we can just ignore this part. What we care about is voltage equal to this. Let me check the answer real quick. That's close.
Do the R's cancel?
It should.
Should the R has to be in meters?
Yes. My answers are within 10%, or within 5%. Just can't really explain why they're not matching.
Value for K, 8.99 times 10 to the 9.
Correct.
Mine says it's within 10% thing.
Is it saying that's correct, or is it saying no?
Saying it's wrong.
Did they use 9 maybe? 9 times something?
What's the
Well,
value?
it's
K?
That would just
don't
make the answer
round.
bigger.
So I don't think I'll look it up.
What's K's value?
8.99, on screen. Oh. Let me. Okay, I have changed the assignment's grading scale so that it should say okay within 10%. If I can only get within 10%, that's just fair.
It says it's correct.
So, within this question, we're looking at the overall potential between two different spots. So here, we we have some amount of potential. Here we have a different amount of potential because it is further away from the field source. And that the different amounts of potential between these two zones is what dictates how a particle within this field is going to move. Electrical potential is what causes electricity to happen. So the difference in potential, we find the potential here, the potential here, and then we solve for the literal difference between them. This difference dictates how fast something here, how hard a particle here is going to get pushed and in what direction. And this is ultimately what happens in a circuit. There's a potential within the circuit, and that potential is what pushes electrons to move through it.
Does the potential change throughout the circuit? Or is
Yes.
it uniform? Like, how do we refresh the potential so that it makes it all the way to the battery?
Well, it does actually it does drain throughout the whole circuit, you're right. How it drains depends somewhat on the circuit configuration. But if this is a 9-volt battery, what that tells us is one side of the battery has 9 more volts than the other. So they might not literally be 9 and 0, but one side is 9 higher than the other one. And because of that difference, current is obligated to move from high potential through the circuit to low potential. And it does decrease throughout the whole process. This is 9, this is 0, and it will drop over various increments throughout. That's kind of how it keeps going, like water running downhill. The water will have different amounts of GPE the entire time, but as long as there's still a lower point to go to, it'll keep going. And we treat it as though when that current comes to a resistor, we treat it as though that jump right here is where that drop happens.
And so a battery is dead when the chemical reaction within it makes it so that on either side of the battery field, there's equal number of charges so that it's not uneven anymore?
It's not so much you're getting to the correct answer, yes. It's not so much number of charges, because charges are constantly leaving one end, entering the other, getting recycled, and then sent back out. It's more to do with how the reaction is setting up each end of the battery compared to the other. So a normal chemical battery creates a reaction that does make electrons loose and free as a byproduct, and it funnels them all towards one side. So that does actually create the imbalance of there being more on that side. And they don't want to be near each other. That's the high potential. They'll move through the circuit to get to the other side, where those electrons get caught back up in the reaction and accelerated back through. Excuse me. Any other questions?
I wrote a bunch of question marks on number 5, but I don't know what my question is.
Well,
The one you took off.
How it completely finished.
I eliminated part B of number 5 because I can't figure out exactly what the intention with that part is. Like, A is okay and B and C is okay, but B, I'm not
I
entirely
didn't
sure.
understand how to do the midpoint instead of like one of
What is the electrical potential at a point midway between the charges?
Okay, so like, it was the first number minus the second number, and they were both over half of the distance, but I didn't understand why you didn't have to do it like twice. Would that be, like, why you didn't have to add them?
I'm having trouble understanding the way that you're saying it. I'm going to draw a picture,
Okay.
start from there. So we have two charges that are creating E fields. And because there's E fields there, there's going to be a certain amount of potential in this one spot. And since they're different since the charges have different signs, the positive exerts field out of itself, the negative exerts field into itself.
They add up.
They will add up. Granted though, if you plug a negative charge into this formula, you will get a different sign from what the positive charge would give you.
So it's like plus a negative.
Yes.
Okay,
You
because
kind
I
of have
thought
to
it was.
reassign the sign based on the picture.
Okay, so if they were both positive, you would subtract them.
Yes. The positive and negative tells you outward or inward from the source charge's perspective.
But
And then looking at the picture,
I'm confused because like the source, like aren't you looking at the midpoint and not either one of the points?
we care about how these fields and the potential adds up at this midpoint, but the direction of the fields at this midpoint depend on what made them. So if we're just considering this along the x-axis, the plus is exerting out of itself, the minus into itself. Even if the formulas give you different signs, though, those are still pointing in the same direction because the formula vector only tells you outward from the source or inward to the source.
The units on this are coulombs and meters.
Yes.
Okay, can you, if it wasn't the midpoint, if it was closer to one or the other, can you explain what the formula would look like instead? Because I think that's where I'm getting confused.
You would plug in different radii for each
What
one.
would you put, so like for the positive number, you would put that distance, and for the negative, you put the other? Okay.
Yes.
Okay, I get it.
And part B, I have omitted on the grounds that even I am not certain what the author was asking for. How do you guys feel?
This is the hardest one I think we've had to do.
I agree.
That's fair. I have observed that myself, and while I'm working on trying to make all the other assignments, cohesive and flow better, we are getting into the more esoteric, harder to visualize concepts. Because up till this point, it's all been forces and movement that you've observed your whole life, thermodynamics that you've studied in other classes. electricity itself is, you've been exposed to it, but you might not have done this math before. And starting next week, we're gonna start talking about magnetism, which, I don't know if you've seen any of the memes or not. Even physicists don't know why magnets do what they do.
See, this is the part of physics that I was not looking forward to.
Yeah.
Well, good news, there's only a couple of magnets chapters before test 2, and then we get to talk about waves for a week before the exam. And I like waves.
This semester is going by really fast.
It really is. On top, like, besides the fact it's been compressed, time is just weird at the moment,
Yeah.
because everyone's experience of everything is currently not optimal. And we're all exhausted, and the entire world needs counseling. Is that one continuous potato?
Yes.
Does
Is
it
it
cut
great?
really thin and then spaced further apart?
Yeah. It's one potato and they've just stretched it out.
Interesting. Why have I never heard of this? That seems like fair food, and
It
yet,
is. But
I've
I
never
wanted-
seen that at a fair.
I want my
Zoom
money.
time.
Yeah.
Gesundheit.
Okay.
You know, we were just talking about, you know, at the committee meeting last night about how we needed to do some crowdsourcing on ideas for like events.
There you go. Potato on a stick.
Is there an International Potato Day?
I'm sure there is.
There has
There's
to
an
be.
International Everything Day. If not, there's at least a National Potato Day.
August 19th is National Potato
So
Day.
if you like split.
That's before
Week
classes
of
start.
welcome. There we go. National Potato Day, potato on a stick.
That's before classes start, but you could just begin the year with, here's orientation and a potato.
Orientation's happening in June, I think. I should probably know the answer to that as an orientation leader,
Prabha,
Yes.
for number 3, what is the electric field within plate? That is just a formula. You just plug things into a formula.
Yeah, I have that exact same question.
And I plugged things into a formula in multiple different ways, and it told me I was wrong every single time.
Well, that's frustrating.
I got 0.018 every single time, and that's obviously way off from the right answer.
Aerobrake capacitors, capacitance with the electric field in place. Okay. Yeah, that should just be C equals Q over, oh, back up.
I just need
Aerobrake. Capacitance.
I tried to use E equals VD.
For which problems?
Number 3.
Hang on, what's the question? So electric field between the plates. How much, do you have these two correct?
Yes.
Okay. Then, capacitance equals charge over E field, I believe is what it said. So, ideally, one would divide this answer by this answer. And that's not correct, as far as web science is concerned.
It's okay, this is how we feel all the time too. You're not alone in your
What is
mind.
the capacitance? How much charge is stored in plates? What is the field?
That
That,
one actually never come open up with some.
Wait, is capacitance and electric field the same thing?
they're not.
12. Now, that was too good.
I mean, wait, yeah, then why are we plugging AN on the bottom of the equation?
Come again?
Then why are we plugging, oh, you solved for, never mind, I didn't realize.
My plan was this.
Well, is.
I did,
I tried that, got 12, and it told me it was wrong.
yeah, I got
Now,
nine.
I'm getting 18, and web science is saying this.
Yeah.
That's sweet.
Where do we get C equals Q over E?
I want to rage quit about the sign right now.
I thought we just don't do web sign yet.
Hey, I recall. Well, I did already pay for it,
That's true. Cost benefit analysis here.
Cost benefit analysis says we don't want to pay for something new, but we still don't want what we have.
It's a sunk cost at this point. I don't know how.
I don't know where that number's coming from.
You mean that's gonna.
It just doesn't make sense. Wait.
I tried to use E equals V times D because it gave us voltage in that question, and I hadn't
Yes,
used it yet.
yes, it did. Oh, I'm getting mixed up. What is that one? Capacitor. Oh.
You wanna share?
Yes,
Fifty
sorry,
or
I'm
we just-
internally processing. Externally processing, I'm processing. Okay, this might not be perfect, but it's at least a start. We know the voltage across the capacitor, and we know how far apart the plates are.
Correct.
So maybe it's voltage divided by plate distance.
Why does that work?
Is plate distance of meters?
Yes, convert millimeters to meters. Okay. This
That
is
works
it.
for mine.
This is the one. Because the other formula isn't C equals Q over E, it's C equals Q over B.
So wait,
I was wondering where that E came from. I was like, I've never seen that one.
I'm doing
It
something
came
wrong.
from the rabid gerbil in my head who flew off his wheel because he's tired.
Wait, you said voltage divided by
This doesn't exist.
the separation?
Yes.
that's still gonna
voltage
be a really
equals-
pretty number.
I'm gonna check the formula.
True.
Voltage drop across something equals E field within it times the distance between the two plates.
Why was I doing voltage times distance this whole time?
Maybe your hamster wheel hamster is tired too, which is valid. I know mine is.
Yeah.
So voltage would be the voltage of the battery.
Yes.
For you, that would be 18.
Yes. I
Divided
divided 18 by .002 and I get 9.
Oh, we're dividing by 0.02.
Yes, the
I
distance, the
see.
plate separation, the distance between the two plates, which is the distance that E field has to accelerate particles.
Wow. Very fun.
So now you use that to find D?
You don't need, you just divide the charge by the area of the plate. So you divide
Correct.
B by the area of the plate.
This is literally charge density, charge per unit area. So B divided by that.
Now, let's see if I can pass the quiz.
I have checked the quiz. I'm going to recheck the quiz.
That wasn't really a jab at you as much as me.
I believe in all of you. At this point, I'm not as trusting of a sign on my own brain. Yes, quiz should be fine. Quiz, I've looked at everything, the questions myself, everything is good.
I thought the quiz was easier than
Looking at the questions on the quiz versus what we've just been talking about, I agree, actually. I actually prefer it that way. I don't want the quiz to be hard because it's something you've never seen before. I want it to be tricky because there's a timer and there's no notes. There's not. You're meant to treat it like this is a little mini practice exercise for a test. Yes.
I'm still doing something wrong on D. You said it's the B answer divided by the A answer?
It should be.
I did that and my response differs significantly from my correct answer.
Did you divide 2.0 time, divided by 1,000 to get meters?
I thought it was just the B answer divided by the A answer.
Yeah, this is already in meters squared.
Oh, sorry, she's doing.
Mine is correct.
In the world?
You're not dividing it by the eighth, you're dividing it by area.
Yeah, it's B divided by, for me, it's 0.6.
Oh, I was dividing by A answer.
Sorry, I realize pointing doesn't really do much unless I'm really being very specific.
Okay, thank you.
So yes, it is charge divided by area. Glad I made this due tonight, as opposed to Tuesday.
And maybe the
Any other questions? How do you guys feel?
Better.
Better is good. Okay. Any questions, needs, comments, concerns, haikus? Before moving on? Now, I will not hesitate to, I will admit, my brain has been really scrambled, really for the past year, 2 years, but especially this past week. So I don't quite remember where we left off in terms of this stuff last time, or where, like what slides I might have skipped. This is partially due to the fact that I'm still making the PowerPoint, because I'm redesigning it and mashing together a few other things, so that this is all of the resistor stuff, and we can move on to other things next week, instead of it being split across 2 weeks.
last thing I wrote was find the resistance of series of parallels.
Okay.
So it's not really anything.
So we did talk about how to find the resistance of the thing. So the 2 things I would like to look at today are how resistance is found for an individual object and also electrical power. So The final completed draft of the notes will be uploaded tonight. There's been a million things going on, so that one's been slipped a little bit, I apologize. Between lecture and lab, we have looked at this formula before and how it affects entire circuits. This equation, V equals IR, does have a name. It is Ohm's law. The same ohms that is the unit of resistance. And it is very important because it is the law for all of circuits. In lab, we took resistors and we plugged them into circuits. I want to briefly look at what makes up and what affects the resistors themselves. There are various factors that determine what a resistor is and how it's going to function. This formula right here is the start of that. The resistance of an object is equal to its density times its length divided by its cross-sectional surface area. And this formula tells us three specific things that affect the resistivity of a specific object. One is what it's made of. Metals inherently conduct better than most carbon-based objects. Most, not all. So metals have a lower resistance because they have, sorry, in retrospect, this is not density. It is a constant that relates to what the object is made of. But what the object is made of does determine its resistance. If it conducts well, it has low resistance. If it resists a lot, then it will have high resistance, and we call it an insulator. That is probably the most important thing to determine how a resistor will function, is what it is made of. Because the same amount of a tiny amount of rubber is automatically a really, really good resistor, whereas even a tiny amount of metal is automatically a very, very good conductor. So, material composition, length, and cross-sectional surface area. In brief, imagine you had two different cylindrical hallways that are the same length, but one of them is just wider than the other. If there were a bunch of people trying to get down one of these hallways, which one would be easier to get down? The wider one. The wider it is, the more physical space there is for things to move through it. That's why if you increase the cross-sectional area of an electrical component, that drives its resistance down. Meanwhile, say we take the short wire and we just make it really, really, really long. Does that make it easier to get through it or harder?
Harder.
Harder. There's more wire you have to get through to get to the other side. So when you increase length, you increase resistivity. It's a little counterintuitive sometimes because increased resistance means reduced effectiveness. So it's okay if one needs to look at the formula for a little while to piece those relationships together. There is, however,
So increasing the area decreases the resistivity?
yes, the wider the component is, the easier it is for current to flow, which is usually why in big industrial settings like power plants and high-tech laboratories, all those cables you see all over the place are way thicker than your laptop cable.
That's true.
Those are the three first things that determine the resistivity of an object. There is one more factor that will affect it, and that is its temperature. You know how computers overheat? One of the reasons they overheat is that for most substances, resistance increases with temperature. The hotter something is, the harder it is for electricity to flow through it. This formula here tells us this resistivity constant for a given material is adjusted based on the object's temperature. So in a moment, we're going to look at how to find the resistivity of an object based on what it's made of. we get the final R answer from this formula, but based on its temperature, this resistivity constant will be adjusted somewhat. So the resistivity equals these factors, which will change it somewhat based on object temperature. And general rule, the hotter it is, the more it will resist. Notice here, this T0 is the initial temperature. If the temperature is rising, then this whole term becomes bigger, which will drive up the entire resistivity constant. And so machines overheat, at least electrical machines overheat, because physically when the wires and the components are hotter, they don't conduct electricity nearly as well. And eventually resistance will increase to the point where current just drops below the required minimum and the machine cuts off. If you're lucky, it'll cut off. If you're unlucky, something will melt.
The alpha term is that given to us?
Yes, so all the variables up here. This is the initial room temperature of the object, and that what the starting temperature is defined by whatever table you get these numbers from. This number here is the base resistivity constant for a material at this temperature. As the temperature changes, you have to adjust this value based on this secondary constant, which also is per element. So there's going to be a table in a second that will show for every single material the baseline at room temperature and then the changing factor from there. And again, since it's different for every single material, you never have to memorize any of them. Speaking of that table, here we are. On this chart, which is the one that I'll be giving you and referring to, this first column is the resistivity constants. That is the lowercase rho variable. So this is the rho, and this is the alpha. This is what is affected by temperature, you can tell from the unit.
So they want temperature.
Wait, the first column is the row and not the second one's alpha?
Yes, rho initial and alpha. And the table tells us these values are set for 20 degrees Celsius as the baseline. So what I usually end up doing, I'll just combine the two formulas more often than not. So I just took that formula for rho and put it in for the rho in the other formula. And ideally, you can use this to figure out the resistance of anything before having to put it into a circuit. Which is handy if you're the one building the circuits and you don't want things to be on fire. It's supposed to be a lower Q is the length of the object. So, quick use of this particular formula. Let's say we're making a resistor, and for the sake of quick math, let's assume this resistor is a rectangle with legs as opposed to a cylinder. Making that quicker. End of your day. We'll continue next week. So, We are told it is made of tungsten. We know its base dimensions. We are asked what its starting resistance is at, for consistency's sake, and I'll add this in. What is its starting resistance at 20 degrees Celsius? You know, okay, I need to rewrite this question because I didn't specify which of those is the length. One sec. Oh. Okay. Rewritten for clarity. Are those? Whatever. Okay. So, our object is made of tungsten. It is this long. Its cross-sectional area is 0.01 millimeters by 0.01 millimeters.
That is the
It is very tiny. Most of the ones in lab were all very small. This might be even smaller though, or at least narrower. So, I was just using resistance equals. We're told made of tungsten. So let's back up one slide. For tungsten, our rho prime is 5.6 times 10 to the negative 8th, and our alpha is 4.5 times 10 to the negative 3rd. Tungsten is chemical symbol W, right? Wolfram.
Yes, let's see, yes.
So material determines rho prime, 5.6 times 10 to the negative 8th. Now, if we're first examining this at 20 degrees Celsius, what's going to happen to this whole middle term?
It's been trying to,
It's just going to turn into 1. Because our prime temperature is 20, our current temperature is 20, this is 0, 8 times 0 is 0, that just leaves us with 1. So when you're at the prime temperature, this fades away and your resistivity constant is left unchanged. I'll leave the 1 in for consistency's sake. But this will all just fall away. Then times L term given centimeters, so in meters, 0.0325. And lastly is the area. We are given millimeters times millimeters. We either need to convert them before we find area, or we find area in millimeters squared and then convert it to meters squared. I prefer the former option. That's everything. We are set to find our one number answer. I'm going to caveat this resistance at 20 degrees Celsius.
So what kind of magnitude should we be looking at for an atmosphere?
18.2. Which, objectively speaking, is a very small amount of resistance. It's more than most wires by themselves, but commercially it's pretty small.
What's like a normal resistance, like in our everyday lives?
Well, the human body is probably several hundred thousand, which is good. You don't want to get shocked.
But what about like the wires around us and stuff?
Wires are designed to be negligible, so smaller than one. Yes. If it's a good wire, it's smaller than one. Sometimes you need like hyper low resistivity in the wires themselves to make sure everything works right, which is where these super chilled server rooms with solid tungsten, really thick cabling come from.
Is there a reason that rats chew wires, or they just do that?
Well, rats will eat anything and everything.
I've noticed pretty much all rodents will eat pretty much anything. I don't know, I'm under the impression some animals have either magnetic or electrical sensitivity. There's a hypothesis that birds have tiny specks of metal in their brains that make them sensitive to Earth's magnetic field, and therefore, which is why they can sense which way is north versus south. Maybe rodents have something similar, and when the wire is next to them, they just think, "Ow, what is it? Make it stop." Or alternatively, they think, "Yes, I want more of that." The only hard evidence I've ever seen is I watched a video of a squirrel walk up to deactivated Christmas lights and chew through the wiring on either side of a big red bulb and carried the bulb away because he thought it was food.
Interesting.
Rodents eat anything. They chewed through screen wiring to get onto my grandparents' porch. Then they chewed through 2 inches of cooler to get to the bird seat inside. Rodents is crazy.
I mean, that's determination right there.
Yes, I admire them for that. Also, though, what the heck? So this is our resistance at 20 degrees Celsius, which is great. If you apply 120 volts to that resistor, what then will be the current it uses?
So it's just 120 volts divided by 18.2 ohms.
Correct. And 120 is a lot, but that is commercially available. Like that is a voltage that exists in machines you use. Everyone agree with about 6.6?
Yes.
Okay. As a reminder, the most dangerous part of electricity is the current. This will kill you. Says me and all scientists, and most biologists. Wait, biologists are scientists. It says me and all scientists.
It's less about like a number that will automatically kill you and more so how long you're exposed to it. Any amount of current can hurt you if it's exposed to you for any length of time. Because since current is charge over time, the longer the time, the more charge. The higher the current though, the faster you reach that danger zone.
So what would kill us instantly?
1 sec. It's not a big figure I keep in my head.
I mean, surely they know that, right, because of the shear things.
I mean, we definitely know.
Wait, is that how they do the electric shear? They set it to.
Also, I was about to ask that.
So this is the top Google hit from the Ohio State University webpage. Any amount of current over 10 milliamps can hurt you, which is to say you will feel it, it won't be nice. Currents between 100 and 200 milliamps, which is 0.1 to 0.2 amps, are lethal.
I've only got now killed.
Yes, that is over 60 times the minimum lethal dose.
Does anybody use the electric chair anymore?
Texas is the only state that it's still legal in.
They
That
use-
sounds painful and terrible.
They
No,
use
Texas is
2,000
the only
volts.
one that they still do it for. You can also still get hanged in Texas.
What the frick?
Yeah, Texas is weird.
I think you can, seal down on fire.
Why are American lawmakers of the mind, well, if it ain't broke, why change it?
The first
Texas
electric
or
chair
here? Oh, really?
used 1,700 volts, but now they usually use 2,000 to 2,200.
Why do they wet the sponge on an electric chair?
I'm sorry, can you repeat that question?
Like, have you ever seen The Green Mile? You know, when they don't wet the sponge and it takes them a long time instead of dying really?
No.
Oh, well, there's like a sponge that goes between their head and the thing. It's like old timey ones, but they
Oh.
would dip it in water and stick it on there so they die faster.
I assume to help conductivity. 'Cause
Yeah,
if
it's a really terrible thing. The mean guy doesn't wet the sponge on purpose and pretends like he forgot.
Yeah, because, okay,
His family.
I hate this, this is less science, but the longer it takes, the more torture you're putting a person through, and without water, it just takes longer.
Yeah.
Additionally, separate figure, human body resistivity is usually about 100,000 ohms. But if your skin is wet or broken, that drops to 1,000 ohms.
What do you mean broken?
Like, if you have an open wound. If the current can get in through your blood, you're 1,000 times less resistant. Your skin is 1,000 times more resistant than your blood.
So could they just like stick a needle in your arm and do it?
Yes, I suppose if they put one needle in one side and one needle out the other, that would expedite the process.
I mean, my thing is, just shoot me.
This says that the electric chair uses 7 to 12 amps.
Yikes,
So that's like 12 times.
that'll
what
boil
it-
you real quick.
Not even. It's like 1,200 times what it takes to kill us.
Don't like that.
Yeah. Yeah. Or 120.
Okay, moving on. I want to finish the example today. Sorry. I like our tangents, but I'm feeling a little time crunch. When you run current through something, it tends to get warmer because you're shooting electrons through it, they're leaving energy behind, it naturally gets hotter. So, which is why your computer will overheat unless it has a fan and a coolant system. Same with cars. So, let's say that we turn this system on, we have this amount of current running through it, which again is an absurd amount of current, so no wonder it heats up quick. This resistor will increase in temperature by approximately 3,000 Kelvin. It warms up to approximately 3,000 Kelvin. What is its new resistance at that temperature? So, our new R, we use the the same row initial, but we now want to factor in alpha and temperature change. Which would look something like this. Oh, sorry, that's 3,000. 300. This term will no longer be 0 because T is now no longer the same as T initial. So when we go to the alpha, the temperature difference, I converted everything to Kelvin, so we end at 3,000 Kelvin, and 20 Celsius should be 293 Kelvin. Is that right? 273 plus 20.
Yes, yes.
The area and length terms are unchanged. This will give us a different, probably much higher number. Yes.
So why don't we change our second one to Kelvin instead of changing our first one to Celsius? Because the alpha is an invert or Celsius module, right?
Correct. But since this is functionally a delta T, this would be the same number Celsius or Kelvin. And since Celsius and Kelvin are the same size, the units will cancel out. So, because of that, like with the thermo chapters, as long as it is functionally a delta T, Celsius or Kelvin really doesn't matter. So I've got final resistance at approximately about 242 ohms.
Mine is 239.
Oh, I put in 273, because that number was still in my head. Okay, 239.9. Is that better?
Yes.
Okay, thank you for catching that. Which is still a pretty small resistance, but from 18.2, it has shot up 13-fold. And so, voltage unchanged with that new resistance, current should also drop 13-fold. We've gone down to half an amp. Which again, still deadly, but if you're running big machines that need this much current, suddenly everything's shutting off. And that, between lecture and lab, is most things how we do with electrical resistivity.
Is there anything that will just automatically shut off when it gets too hot, like on purpose?
Most systems that have something in them that could go wrong are designed to turn off automatically. The example that I keep using is a fusion reactor. The current prototypes for those have a bunch of machines that are designed to create plasma and then accelerate it around a metal donut, basically, to get it up to high speed and then slam it into other hot plasma to replicate the conditions on the surface of the sun and try to fuse the atoms together. If any part of that goes wrong, suddenly there's hot sun plasma all over your lab.
Don't phones shut off?
So
when they
does it
start?
turn off because
Yes.
of this, or does it turn off because it's just programmed to turn off?
Both. Something fails when it overheats. And ideally, there's systems in it to recognize that is failing, let's shut the rest of it off before something melts. I kept you guys longer than I was supposed to, I'm sorry. There is still some of this material that I'd like to discuss on Tuesday, so I'm probably going to make the 17 assignments due next Thursday. So we can finish up 17 on Tuesday, talk about any questions that come on Thursday.
When you said the 17 assignments, I was thinking 17
Chapter,
different
assignments
assignments.
about
I was like,
chapter 17. For now, 16 to tonight, focus on that. We'll finish up 17 next week.
I have one more question.
Yes?
Is like something like this with an electric stove would work? Is making it really hot?
Do you mean, there's two types of electric stoves. The first one, yes. When you run current through this specific heating element, the element just gets hot and it's designed to do that. Now, there's a different type called an induction stove, which works on magnets instead.
Was that, well, I guess we'll learn about it in magnets.
You know what, I showed the other lecture that video, I didn't show you guys. I had a video pulled up, and I'll show it again next week. So, based on the title, what's about to happen is this person's putting a sample of iron in a copper coil. There's currently electricity in this coil. Wires with electricity running through them create a magnetic field. So right now the iron's being held up by magnetism. And
That's so weird that it could just do that.
yes, electricity and magnetism are different, but they are intrinsically linked. One creates and affects the other.
What did you think the pencil there for?
I think it's just to keep it straight, keep it in a specific location, because any minor warble might send it careening out of the way. And it's slow at first, but the magnetic field is not just making the iron move, it is also causing all the particles in and around the iron to start moving. So energy from the electricity in the coil is kind of being sent wirelessly into the iron, just because of magnets. And because it's going to start getting hotter, it's just going to start melting.
Well, why then, in one of those stoves, does it not, like, just melts the metal and then it's not only used once? Why is it good every time?
An induction stove is designed to use magnets to heat up a metal pot on it to a very specific degree.
Oh, okay, I was thinking there was metal inside the stove that was heating up.
No, an induction stove doesn't get hot. An induction stove turns on a magnet, and then that magnet affects the metal pot you put on it, like this.
I see. Never heard of that kind of stove before.
It's becoming more common. I've had students start asking about it. And I'd say the other type of electric stove is far more common. It's the type that I own. And that one, yeah, it's like a light bulb. You run current through something, it physically gets hot, that heat does the boiling.
Thank you.
You're welcome. And eventually, when iron melts, it loses its magnetic properties.
Ah. That's fancy.
Yeah.
That's really cool. I didn't know magnets could do that.
Magnets can do a lot of things, and we don't fully understand most of them.
Nice. That would drive me insane.
Oh, yes. If you ever want to make a physicist mad, like if you go to someone's like capstone or thesis presentation and they give their presentation, they ask you have questions. If you stand up and ask, how would this be affected by magnetic fields, everyone in the building will rage quit.
Okay. Noted, if I ever want to make someone mad. All right, see you in lunch.
See ya.